Okay, so today I'm going to focus almost the whole lecture on just one thing, which is the MM1 Queue. And okay, there's a chair over there if you want. MM1 Queue is sort of the bread and butter of queuing theory. You know, if you don't know what you're doing, just try the MM1 Queue, because you know, in some sense, everything you do in queuing theory is approximate anyway, right? Because you're making all these assumptions about arrival and departure processes that are not quite right. So if it's going to be wrong anyway, then why do you spend a lot of time on it, right? So if you don't know what you're doing and you want to get a sort of just a rough idea, which is what you'd expect to get anyway from queuing theory, it's useful to apply the MM1 Queue. So in many ways, what we've been building to in the last 4 lectures really has been to set all the foundations in place so that you can understand the MM1 Queue. Okay, so you have to understand stochastic processes, you have to understand the notion of birth-death process, and you have to understand a little bit about Poisson process. All of these are just so that now you can understand what MM1 Queue is, and this MM1 Queue analysis will, we'll develop that into MM infinity, MM1K next lecture, and MD, and sort of give you some idea into the GG queue, the general queue. And these names do not make much sense for you now, but they will in about a little bit. But what I'm trying to point out here is that this is sort of the basic thing you need to know. So if you understand the MM1 Queue, you understand sort of elementary queuing theory. Okay, you don't understand queuing theory, but understand elementary queuing theory. And if you understand this well, the rest of queuing theory, which is quite complicated, will be easier to understand. Okay, so this is like the ABC of queuing theory. This is it. ABC of queuing theory is MM1. Okay, so you can quote me on that. All right. So to get started, I want to just review briefly the general equilibrium solution for a birth-death process that we kind of finished up with last time. And I'm going to talk about the convergence, which I did not talk about last time, because that's actually pretty important. And then that will immediately allow us to solve for MM1. Okay. All right. So a birth-death process is a stochastic process, and it's a homogeneous stochastic. What on earth is going on? Okay. All right. So a birth-death process has this property that from any state I, we can just go to state I plus 1 or I minus 1. And so a transition from a state to the next state is called a birth, and a transition from a state to a previous state is called a death. And as I said, it represents, generally speaking, a population, and the state value I is the size of the population. And so we're looking at the population that grows and shrinks. And as we'll see in a bit, when you talk about the MM1 Queue, what we're talking about is the queue growing and shrinking. Okay, so population size is exactly the same as the number of people in the queue. And so arrivals to the population happen according to the birth process. We go from state I minus 1 to I, or I to I plus 1. And then departures from the queue due to service happen in this direction, and that's the departure process. And so just as we go through this, keep in mind the queue in front of the Tim Hortons, in the Davis Center. So people arrive, the queue grows longer, they get served, the queue shrinks. And so that's exactly the birth-death process over here. Now, in order to study the birth-death process, we looked at first the pure birth process, and that was a Poisson process, where essentially the arrival rate is lambda at every state, and it's state independent. Okay. But it's the same lambda for everything. Okay. Now, we found that a system like this is actually a system where every state is transient. We never actually stay in any particular state. We just keep moving from state to state. And the parameter of interest really is the probability of being in any particular state at a given point in time. So PIT is the probability of being in state I at time t. And we found that this was described essentially by a Poisson with parameter lambda t. Okay, so we're going to move one step ahead, and now we're going to consider essentially a general birth test process. And in the general birth test process, the arrivals are over here is lambda I minus 1, lambda I, etc. And the departures over here are mu I plus 1. I guess I don't really need that. I just wanted to show it's potentially infinite in both directions. So I'll just draw this to show that it's potentially infinite in both directions. Obviously, it's going to be a zero state where you kind of bottom out. You have no arrivals, so you have no departures from a zero state. So this is state 0, so it's semi-infinite. To come up with the probability of being in any particular state, the state equations, the equilibrium state equations, what we're going to do now is we're going to assume for just a minute that the system is convergent. It's not unstable. So in other words, that every state is recurrent. Okay, we don't have transient states, and I'll come to the condition for that in just a minute. So we use the technique of balance equations, and we can just start with the 0th one over here. So let me draw that part over here. So here's 0, and we're going to 1. So we go up at rate lambda 0, we come down at rate mu 1, and we can write down that at the steady state, in equilibrium, we can say that lambda 0 p0 equals mu 1 p1. Okay, this is just the balance equation. And so I'm just showing that last time we showed that this balance equation is achieved by looking at the QJJs, the transition rates, which are defined as the infinitesimal transition rates, the limits of the straight transition probabilities as we take the delta t parameter going to 0. But as we discussed last time, we don't need to do all that machinery. We can just pretend that all that math doesn't exist and just, kind of mechanically write down the values simply by associating this equilibrium state with P0, this equilibrium probability. The equilibrium probability in being state 0 is P0, the equilibrium probability of being in state 1 is P1, and just kind of blindly writing down lambda 0 P0 equals mu 1 P1 as the balance of the flow of probability into and out of a state, and the requirement that in equilibrium the flow of probability entering a state and leaving a state must balance out. And this is a very general technique. You can use it in any stochastic process, actually. Okay, any stochastic process in equilibrium. That is, if the stochastic process has equilibrium, which means it has to be ergodic. So if it's not ergodic, we're out of luck. But if it's ergodic, we can actually talk about the limiting probabilities, and we can use the balance equation technique. So I'm just using that to write this down over here, which immediately gives us a P1 equals lambda 0 by mu 1, P0, all right? And we can now use this to solve for P2 as a function of P1, and so on. And what we get is P2 equals lambda 0, lambda 1 over mu 2, mu 1, P0. Okay, it's easy enough to show this. Probably can try that at home. And in general, we can find that Pj, probability being state j, at equilibrium is nothing more than P0. The product I equals 0 to j minus 1 lambda I by mu I plus 1. Okay. All right. So that is the definition. That's how we get Pj as a function of P0. And then finally, we know that sigma Pi equals 1 because it's a probability distribution, and immediately gives us that P0 plus P1 plus, okay, whatever P equals 1. And then we can write each of P1 in this fashion. Okay, so what we get is that P0 plus P0 lambda 0 by mu 1 plus P0 lambda 0 lambda 1 by mu 1 mu 2 plus equals 1. And all of them have P0 as a common factor. So we find that P0 times, okay, if you just expand it out, we get that P0 equals 1 over 1 plus, so that 1 comes from this one over here. And then all of these other terms essentially come from here. All right, we can just write it out as sigma j equals 1 to infinity, P pi I equals 0 to j minus 1 lambda I by mu I plus 1. So this is sort of where we got to last time. And before I go on, I just want to make sure so everybody is comfortable with the derivation of this equation over here, P0 and for Pj, because at this point we basically have everything we need for the MM1 Queue. So I want to make sure we got here. So any questions about this? Okay. At all about? Okay. So given this, we can now ask the following question: does this converge? Do we actually know that the probability 0 exists? Because after all, we have an infinite sum over here. And one thing you have to be always careful of in anything to do with math is be careful of infinite sums. They can be very tricky, okay? And I wanted to actually give you an example of this just because, okay, so I think we talked about one of these. So we know that 1 plus half plus 1/4 plus, well, this is a convergent series. This converges, okay? This converges to the value 2, okay? So that's great. But things are not so obvious. What about 1 plus half plus 1/3 plus 1/4 plus? We discussed this. Anybody know? Is it converge or diverge? It diverges, okay? So this is sort of non-intuitive, okay? At least to me it's non-intuitive that it diverges. So this converges, this diverges, and then here is a series that I always have fun that this is 1 plus 1 minus 1 plus 1, sorry, minus 1 plus 1. So does that converge or diverge? So you can actually prove that this sum is equal to 0 or 1 or minus 1, depending on how you put the parentheses. So if you, this is basically what you can, actually you can make it equal to 2 as well. So it's 1 plus 1. Actually, I should start with, I got this wrong. So I have to do 1 minus 1. Let's just do it like this. So 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc. So if I put the parentheses like these, it's just 0 plus 0 plus 0. So it's 0, right? If I put the parentheses like these, it's 1 plus whatever, so that's 1 plus 0 plus 0, so it's 1. And similarly, if I make it, I have to choose the parentheses carefully, I can get minus 1 as well. Okay, I'll leave it as a homework exercise. Figure out how to make it work. Okay. What's happening is that this is a thing that oscillates basically between, actually this could be 1 or 0. It won't get to minus 1. It oscillates between 1 and 0, so it goes like this. And yeah, okay, so we don't have convergence. So anyway, this one converges, that one diverges, this one oscillates. So when you start looking at infinite sums, and this has given mathematicians a headache for hundreds of years, not just recently, but for hundreds of years, what is the meaning of convergence, okay? And this is intimately tied to the meaning of a number. What is a real number, right? A real number actually turns out to be an infinite sum, because if you take a real number and write it out, let's take 1.23456, whatever it is. It's 1 plus 2 over 10 plus 3 over 1000 plus, etc. Right? 3 over 100, 4 over 1000, and so on. So it's an infinite sum. What does it add up to? It adds up to some kind of number, but is it a convergent thing? Well, intuitively it's convergent, right? But what does it mean to say that a real number is a convergent series? So in the theory of numbers, the formulation of a real number itself becomes quite problematic, because if you don't know what a number is, I can't tell you whether something is greater than or less than a number, because I have to tell you that this number is greater than the sum of an infinite series. So though it looks kind of exotic to say, well, why are you considering sums of infinite series? Even a real number is actually a sum of infinite series, okay, trivial infinite series. And so even concepts like greater than or equality become problematic. For example, this is an interesting aside, 1.99999, it goes on. Is this the same as 2? Why is it the same as 2? I mean, it looks different. So again, what I'm saying is that is 2 greater than this or not? right? Because I said if you don't know the meaning of number, I can't tell you what the meaning of 2 greater than 1.99999 whatever is, because is it greater or is it lesser? Is it the same? Okay, so these kinds of problems are actually quite fascinating. If you're interested, there is a book called Number by a guy called Danzig, which was written around 1930 something, and it's just about numbers. The whole book is just about the concept of number, and it starts with you know, obviously integers, but then gets into this, and the I think it's the Dirichlet Schnitt, the cut. Anyway, but these kinds of problems are pretty interesting. So whenever you see an infinite sum, watch out. You know, there is something hidden over here. What's hidden over here is that we have to make sure that this infinite sum actually converges. And what's going on here is, here at birth test process, there are some set of arrival rates and some set of departure rates. So just think about it intuitively what's going on. There is arrival rate at a particular state. It's a state-dependent arrival rate over here. It's not state-independent. And we're getting these arrival rates coming over here. If at some state I, we find that people are coming in faster than being served, what's going to happen to the queue? It's going to grow, right? We're going to have some barrier beyond which, you know, service is happening fast enough. Otherwise, we're going to be in trouble, okay? So we need to find the condition for the existence of this sum. And without going into details, it turns out that there is such a condition. And the condition for convergence is the following. There exists some value J0 such that for all j greater than J0, mu j is greater than lambda j. Okay, and it's a strictly greater than lambda j. In other words, we allow the population to grow and grow and grow till it gets to some sort of barrier J0. Once it gets to J0, okay, somewhere over here, after this we say enough is enough. Okay, I'm going to have to start serving people faster. And if such a J0 exists where mu is greater than lambda, mu j is greater than lambda j for all states beyond this, then we can be assured that this sum over here converges. Okay, we don't need the J0 to be at 0. It can be, you know, at 1 million. But at some point we've got to draw the line and say, that's it. We're going to have to start serving people faster. And if that is done, then we can assure ourselves that P0 exists. And if P0 exists, the Pj's exist. That's trivial. And so the birth test process turns out to be a stable one. All right. So how do we compute these? I'm going to do an example here just so that it's clear in your head. So I had I think figure 6 in the notes we had a simple birth test process over here. So here are the 4 states: 0, 1, 2, 3, and we had the following transition rates: 1, 5, 4, and 5, 8, 10. So the way we solve it is we got to first solve P0. Okay, if you don't have P0, you're out of luck. So let's go find P0, and we have this equation for P0. All right. Now I should point out that this is a finite birth test process. Okay, because it's a finite birth test process, we don't have to worry about transient states. It's ergodic by definition, and with ergodicity, these transition rates exist. We have to only worry about transients when you have infinite chains. Okay, finite chain by definition is recurrent, and if it's recurrent, and obviously, the corresponding probabilities are all going to be non-zero. So we have irreducibility. This is ergodic chain, so we can just kind of plug and chug over here. So how do we solve for this? Well, we say that P0 equals 1 over 1 plus, well, we can pretty much read off the values, okay? 1 over 5 plus 1 over 5 times, so this is 1 over 5 times 5 over 8. You can just sort of read off lambda over mu as those values, 4 over 10. Sorry, 5 over 8. Plus 1 over 5 times 5 over 8 times 4 over 10. Okay, and that equals, well, 0.73. Okay, it just turns out to be that way. Again, just as a sanity check, you should look at the values here. The rates over here are much slower than the rates of service. The rates of arrival are much slower. So what is the chain doing? It's pushing you towards 0. If you leave 0, you're going to be pushed back with 5. If you manage to escape, you're going to push back with 8. If you manage to escape, they're going to push back with 10. So it's pushing you all the time towards 0. If it's pushing you towards 0, you expect P0 to be pretty high, and it's 0.73. Now you can plug this into P1. So P1 equals 1 over 5 times P0, and that's just a fifth of P0 is 0.146. And then similarly, you get P2 equals 5 over 8 times P1, which is 0.09, and P3 equals 4 over 10 times P2 equals 0.0365. All right, so, and you sum them up, they'll of course sum up to 1. So you can see that once you write down the birth test process in the form of a state transition rate diagram, there's not a state transition diagram, it's a state transition rate diagram, you can pretty much write down the equations for the equilibrium just with these two equations, okay, and that's it, we're done, okay. So we know the equilibrium probability of being in each particular state. Any questions about this? Yes?
Why do you put that condition that at some point J, when find that J, you should have that ratio less than 1?
Why do we need the convergence condition? Otherwise, we don't know that if this is going to exist, that the sum is going to exist for infinite birth depth processes.
Because, I mean, from just the series point of view, you should have the limit as n goes to infinity of an plus 1 over an to be less than it. That's where they derive that condition.
That's correct. Yes, and it turns out to be equivalent to this, as far as I know. I mean, yes, all you want is that this condition, you should be a convergent series. Okay.
That's what I'm saying.
Yeah.
Even if it says infinity and we still have that condition, it's convergent.
So what's the question? I'm confused now.
So why are we restraining that to a finite J? Even if J goes to infinity and we still have that condition, the series is convergent.
So this requirement that after J0 is a weaker condition than requiring it for all J, right? I'm just requiring it after some value J0. It's a weaker requirement. I can say for all J, mu J is greater than lambda J. Okay, that's not required. I just need it after some J0. So it's a weaker condition. Obviously, if it's true for all J, then J0 is just 0 and you're fine. Okay, it's just a convergence condition. Yeah. Okay, so I'm going to stop here, I guess, and take a short break, and then we'll come back to the MM1 Queue, unless any other questions over here. Okay, let me stop here and move on to sort of actual queuing theory now, and we're going to spend pretty much all the rest of the time on the MM1 Queue. So what is MM1 anyway? What does it stand for? And this notation called, which is of the form A/B/C, is called Kendall notation. It was invented by a guy called Kendall, and it's a shorthand for describing the arrival and departure processes and the number of servers. So A is the arrival process, and the B is the departure process. And by process, I mean stochastic process. Okay, so the arrival is stochastic, it's a stochastic process. B is a departure process, it's a stochastic process, and C is the number of servers. Now, there are extensions to this. You have, sometimes people use D, which is the number of buffers, and then you have E, which is the service discipline, whether it's first come, first served, or round robin, or whatever. But almost always we just see ABC. We just say MM1, and then the rest, we don't really care. But when we say we don't really care, what it means is that the number of buffers is typically assumed to be infinite, and the service discipline is assumed to be first come, first served. So if you want to change those assumptions, then you would say something else, right? But other than that, if you say MM1, means MM1 means, well, what it means I'll tell you in a minute, but you assume that it's infinite buffers and service discipline is first come, first served in the queue. All right, which is your Tim Horton service discipline, right? You just serve in order of arrival. What does M stand for? So M means Markov, and D is deterministic. And G means general. That's the shorthand. And pretty much this is all you'll see. Okay, pretty much all you'll see is M, D, and G. Markov means that the process is a Poisson process. Now, one could argue it should be called P and not M, but Kendall is dead. I can't argue with him. So it's too bad. It's why is it called Markov and not Poisson? Actually, I don't know. Okay, that's just the way it is. And as I said, it's too late to argue. So when you say M, you really mean it's a Poisson process. D means deterministic. What does deterministic mean? It's a deterministic process. Things happen exactly on time. So, for example, you have packet arriving exactly 1 second. So every second, packet arrives, exactly on time. That's deterministic. General means we don't know. Okay, general means it's something that's not Poisson and it's not deterministic, and we don't really know. We can characterize it in any number of different ways, but this means, general means like you're out of luck. Okay, because analysis of anything with a G in it is just super complicated. You'll spend years of your life figuring it out, and then in the end you'll find out all your assumptions were wrong anyway. So, which is why MM1 is it's a good sort of Swiss Army knife. It's wrong, but it's wrong, but it's easily wrong. Okay, if you're going to do something wrong, it may as well be easy. Okay, there's no point in doing something wrong that's complicated, because you're wasting your time and it's wrong anyway. So if you know it's wrong, just do something that's easy. It's just a good skill to have. Okay. All right. So I said that the MM1 queue has a Poisson process. So, well, if you remember, a pure birth process is Poisson, right? So if you look at a birth-death process where the arrival to each state is always lambda, independent of the state, then that's essentially a Poisson arrival process, just ignoring the death, the departure process. Okay, departure process is the death process. All right, so we ignore the bottom half, and that's a Poisson process. So this looks at least reasonable from the perspective of MM1. So at least you got the first M. What about the departure process? Okay, I'm going to state here without proof that if the departure rates are mu and state independent, then the departure process is also Poisson. Okay, and actually it's a homework exercise, so you can prove it, and the proof will be in the homework solutions. It's not actually particularly hard to show that if the departure process is state independent and mu, then that's also Poisson. And of course we have one server. We only have one server over here because the service rate is only mu, and that means it's got one server. Okay, so an MM1 queue is nothing more than a birth-death process where you have arrivals of lambda and departures of mu, and the arrivals and departures are state independent. Okay, so that means that to analyze the MM1 queue, all we really need to do is to take the general equilibrium solution we saw earlier and remove the conditioning on state. In other words, where we had lambda 0, lambda 1, etc., it all becomes just lambda. So it's actually much easier. And similarly, we have mu 0, mu 1, etc. You just put mu. Again, it's much easier. That's why the MM1 queue is so easy, because all of these state-dependent arrival probabilities go away. Okay. Any questions about this over here? So intuitively, what's happening is that we have arrivals happening which are independent of which state you're at. So no matter what state you're at, there is a constant rate of arrivals. That's why it's Poisson. And no matter what state you're at, you have a constant rate at which you depart. Okay, departure to the previous state, in other words, queue service rates are going to be independent. Now, what this also means is immediately that the inter-arrival times are exponentially distributed, and the inter-departure times are also exponentially distributed, because that's a characteristic of the Poisson process. Okay, so what does this mean again? That means that the time that it takes for a server to serve one customer is going to be chosen from an exponentially distributed distribution. Now, one has to think, is this really true in a computer network? Okay, so what happens in a computer network? We have a server, and remember we draw servers like this. We have a circle, we have a queue, and we have packets in the queue, and we're serving it in this fashion. If the customers are coming to Tim Hortons, we can argue that the service rates are exponentially distributed. Service times are exponentially distributed. Why? Because somebody comes in, they order something small or large, okay, and it can take a very long time, okay. So it's exponential. But if you look at a packet, the packet service time is nothing more than the packet size divided by the link capacity. All right? The packet size is the size of the packet. Now, what are the packet sizes on the internet today? Well, most packets on the internet today, in terms of volume, are actually very small. Why are they small? Because they're acknowledgement packets. Okay, if you're doing TCP/IP and you're sending acknowledgements, they're 40 bytes. Okay, so it's just the header. There's nothing else. The TCP header is 20 bytes. The IP header is 20 bytes. You've got 40 bytes, and you chuck it into the internet. So you got a pretty big spike at 40. And then the maximum, if you look at the distribution of packet sizes, at 40 you have a spike. At about 500, roughly, you have another spike. And 1500, which is the largest Ethernet frame, you have another spike. Okay? Why? Because you understand the largest possible packet on the LAN, and then it goes into the internet. Why is this spike at 500? Because historically, the internet required that every link carry at least 576 bytes. Okay? Why 576? It's another historical lesson. I'm not going to go into it. But anyway, so people said, okay, we'll fragment it into 500 bytes so it won't get broken up. So anyway, if you look at a link, you pretty much have a trimodal distribution around these values. And so what about the service distribution? Well, the link capacity is constant. So the service distribution also looks like this. So the service times, if you will, look like this. For 1500 bytes, you have a long service time, a medium service time, and a short service time. Okay, and you have these three service times, and all of the service times essentially don't even exist or are very small. This doesn't look exponential to me. Right? It doesn't look exponential to anybody else either, which is why I've been saying all along that Poisson departure rates, or Poisson is a pretty much not a correct distribution. It's not a valid representation of this kind of thing, but it's simple. Okay, we'll see how simple it is. So 2 points to take away. First point is that by drawing this in this fashion, I'm making a very strong assumption on the inter-departure times, or the service time distribution, which is incorrect. Okay, it's incorrect because of the packet distribution times, and so you need to correlate this graph of the packet size distribution with this mu over here and see that they don't match up. Okay, because this is telling you that the inter-departure times are going to be Poisson, they're not. So inter-departure times are going to be exponentially distributed, and they're not. Okay, and the second thing is that over here is that, okay, but if you make this assumption, things become much easier. So let's go into the much easier part, setting that aside for now. Okay, any questions about this over here? Okay, so the inter-departure times look more like, three deterministic processes rather than exponential, actually. But anyway. To come back to this, so this is the Kendall notation. So what I'm going to state here is that the MM1 queue is exactly this. And it's exactly this because arrivals are Poisson. We already saw that. Departures are Poisson. You prove that. And we have one server. Okay? So analysis of MM1 queue becomes nothing more than analysis of this birth-death process, which has state-independent arrivals and state-independent departures. Okay? Any questions about this at all? Yes?
So what about this? Represents the fact that it's one server?
If you have two servers, it becomes 2 mu.
Okay.
Yeah. If you have two servers, you have 2 mu. If you have 3 servers, you have 3 mu, etc. Okay. Yeah. So that's what you're doing, right? Increasing the departure rate by the number of servers, depending on the server speed. Okay. So let's go analyze this queue. And when you say analyze a queue, what does it mean? Okay. So what we mean by analyzing a queue, any queue, is to find out this value, the equilibrium probability of being in a state. Okay. PJ. The probability of being in state J in equilibrium is the meaning of analyzing the queue. Why is this? First, we need to assume that the queue is ergodic. If the queue is not ergodic, if it's transient, then there's not a whole lot we can do about it. We can tell you the time delay, the probability of being in a particular state at a particular point in time, like we saw the pure birth process, but there's not too much you can learn from it, okay? So, assuming it's ergodic, once you get Pj, everything else just follows from it, okay? For example, if you know in state J, a certain metric is there, we just multiply Pj with that metric and we just sum over all the states to get the value. Okay, so I'm going to demonstrate this for the MM1 Queue. So first I'm going to compute Pj, and then after that we'll see how the mean number of customers and mean waiting time just follows straight away from knowing value of Pj. So once somebody gives you Pj, everything else is basically just plug and chug. All right. So what is Pj for us? Well, we remember that P0 was going to be. The Pj is going to be P0, okay? And then here we can just say lambda by mu to the j, because the product that we had earlier was lambda 0 by mu 1, with lambda 1 by mu 2, etc. Well, all of those are the same, so it just becomes lambda by mu to the power j. And P0 becomes 1 over 1 plus sum j equals 1 to infinity, lambda by mu to the j. This is the same equation written over again. And it turns out that if lambda less than mu, that's the convergence condition. So remember that we had to have some j0 where lambda is smaller than mu. Well, over here, all lambdas and all mu's are the same, so it's got to hold for every state. So if lambda is less than mu, then this value over here is nothing more than okay, so this whole denominator becomes 1 over 1 minus lambda over mu, okay? Why is that? Well, this is 1 over lambda by mu plus lambda by mu squared plus lambda by mu cube, etc. And if you just look at that, lambda by mu represented with the value r, it's 1 plus r squared and so on, right? That's an infinite sum, 1 over 1 minus r, where r is lambda by mu. So denominator is nothing more than this value over here, 1 over 1 minus r. And this becomes, which means that P0 equals 1 minus lambda over mu. Okay? So that's what we're saying over here, is we've derived for the MM1 queue the probability of being in state 0, the probability that the queue is empty, nothing is going on. Okay, so let's understand that for a minute. So lambda is the arrival rate and mu is the departure rate. Okay, we define the value rho as being lambda by mu, and we call this the utilization. So the utilization of the queue intuitively saying, look, I'm arriving at the rate of, let's say, 5 customers a second and serving them at the rate of 10 customers a second. On average, the utilization is 0.5, okay, 5 over 10. So what we're saying is that we can intuitively look at the workload, how busy is the queue, as just the ratio of the arrival rate to the service rate. Okay, so these are, we got lambda and mu, by the way, in the beginning as the probability of transition from state to state plus 1. It was basically qj, j plus 1, which was nothing more than pi I plus 1 delta t over delta t as limit as delta t tends to 0. Okay, this equals lambda, right? So we're looking at the infinitesimal transition probability from the I to the I plus 1 state, okay, or any state to the next state. So looking at the infinitesimal transition probability, it turns out, and it's intuitive and it can probably be proved, that this is exactly the same as the arrival rate, okay, of entering the queue. Okay, if I say packets arrive at 5 packets per second, that is your lambda. That is in fact the same as this, okay, because you can translate from that rate into the infinitesimal probability of transitioning from state to state in the underlying continuous Markov chain. Okay, so again we're going to make another simplification. It's mathematically well founded, but it saves you from thinking. All you say is that whenever I have arrival rate of packets per second or customers per second, whatever, we immediately say that is lambda. We don't have to go back and figure out the infinitesimal probabilities at all. We just say, okay, yeah, that's the customer arrival rate, and that's the service rate. Okay, we can just kind of plug that in directly into the queue. Again, it saves you some amount of effort. And so intuitively, it should be clear that lambda by mu is the utilization. Okay, if the arrival rate is the same as the service rate, for example, every time somebody comes and somebody is being served, they're both matching, right? We can say utilization is 1. It's 100% use. What happens if more people come than are being served? We'll say utilization is greater than 100%. Okay, so there's a natural or intuitive correlation that is defined in this way. We can then write down that P0 equals 1 minus rho. Well, this is a nice thing to have. What it says is that the probability of being in idle state is 1 minus the utilization. The utilization is 90%, have 10% probability of being in the idle state. Again, that makes intuitive sense. So two observations. The first observation is that the probability of being in the idle state, you have no work to do. P0 means no work to do. You know, people are just sitting there taking a break. This is independent of lambda and mu. It only depends on the ratio. So it doesn't matter whether there are 1,000 people arriving per second and the departure rate is 2,000 per second, or it's one person arriving per second and departure rate is 2. It doesn't matter. It just matters. All that matters is the ratio. Okay. So this is a very interesting result. It means all queues or all MM1 queues which have identical values for lambda over mu or identical values of rho behave the same. Okay, we cannot tell the difference between them. They all look the same because probability of being in state 0 and consequently the probability of being in state j, which also is nothing more than 1 minus rho to the j, okay, also only depend on rho. Okay, so the essentially the parameter of interest just becomes rho for the MM1 queue. Okay, and that immediately gives us all the state probabilities, all the PJs. Again, another interesting point is that this is true for all queues, all queuing disciplines, I should say. With unbounded queue sizes. In other words, if you have an infinite number of buffers, we'll always find that P0 equals 1 minus rho. If you have a finite number of buffers, what happens is that we can lose our arrivals in the following fashion. We have a finite number of buffers. It means that you have a limit to the size of the chain. And any arrivals that happen over here are going to be lost. Okay? So in some sense, our utilization goes down. Okay, because we're losing people. People arrive to the, let's say Tim Horton says, we only allow 20 people in the queue. If you're the 21st person, sorry, you can't come in the queue, you have to go away. That means some arrivals are lost. When some arrivals are lost, the utilization goes down, so we can't use this equation anymore. But for all unbounded queues, P0 equals 1 minus rho is true, and that's true for GG1 queues as well. So that's one of the few things we know about GG1 is P0 is 1 minus rho. Okay. All right, so last point I want to make here is that this one, 1 minus rho to the j, well, that's just a geometric distribution. Okay. It's just a kind of interesting fact to observe. That means that as we look at the states and look at the probability of being in state 0, state 1, state 2, etc., you're going to see essentially a geometrically declining discrete random variable which defines the probability of being in that state. You know, it's not exponential, but it's a discrete probability. You kind of have smaller and smaller values going away from 0. So 0 sort of is the most likely state, and we go away. This is what we meant by saying that queuing theory is about transients. Most likely, okay, it depends on lambda and mu, of course. Most of the time you want to be here, 0, nothing happening. Some people come in, you go into the queue, and you go back over here. You have some more queue, you go back over here. All right? So the queue, in this sense, queuing theory is a study of transient behavior. We have essentially an idle system. We go out and you come back. Okay? In this chain, you kind of make excursions back and forth, back and forth. All right? And we want these excursions to be small. Our goal is essentially to keep the system nice and clean. I'll explain what that means precisely when we talk about the mean number of customers and mean waiting time. But the intuitive understanding is not that we should have queues, but that we should design systems. So generally speaking, queues are small. Okay, nobody wants to wait. So the whole kind of intuitive thing we want to do over here is to design the system, that is, design the service rate and the scheduling discipline such that, generally speaking, we're in P0. We want to make P0 high. Okay, and the geometric distribution says that for MM1 queue anyway, that's really what it's going to be. Most likely, depending on the parameters, the highest value of probability is for P0, and you have declining probabilities for P1, P2, etc. So we just make these excursions away from 0 and back to 0 again, and that's really what we're studying over here, the transient phenomenon. So I started up by saying that, and now this equation is a precise statement of the fact that queuing is a transient phenomenon. The probability of being in state J is a geometrically declining value. Okay, so we're going to make very small excursions, and the probabilities of being far away from P0 are, of course, correspondingly small. Okay, any questions about this? Okay, so there's a numerical example in the, maybe I should do the example that kind of gives some idea of how to model a real system. Okay. So what we want to do now is just to give some idea of how to analyze a real computer network. So I'm going to analyze the following system. So I have a link, and it has a capacity of 1.5 megabits per second. This is often called the T1 speed. This is a standard speed. If you go to Bell and say, I'm a business, give me a data rate, they'll say, yeah, how many T1s do you want, or T3s, and so on. So T3 is 45 megabits per second, but T1 is sort of typically what you buy, so that's a reasonable number, 1.5 megabits per second. And I'm assuming that the mean packet length is 500 bytes. So that's pretty reasonable. As I said, one of the three maxima in the distribution is at 500, or roughly 500. And I'm going to assume that the packet arrival rate is Poisson. Now that's this approximation, and lambda equals 300 packets per second. Okay. I want to know what's the probability the queue has one packet. Okay. Okay, assuming that it's exponentially distributed inter-departure time, or it's MM1 queue. So we just assume it's an MM1 queue. So first of all, let's go back and think about this for just a second. So somehow you instrument your small company. You buy a T1, and you want to know how many packets are going to be in my buffer. So you can measure the mean packet length. That's not particularly hard to do. You can just start off Cisco NetFlow. It will tell you, yep, you're sending packets, your mean packet size is so much. It will also tell you the mean packet arrival rate. Presumably, you're doing the computation over the busiest hour of the day, because that's when you size things. So you find the busiest hour of the day is between, let's say, 10 and 11 a.m., and you measure the packet arrival rate, and it tells you 300 packets per second. Now what we're going to do is we're going to make some simplifying assumptions. We're going to say, look, we know that the packet arrival rate is probably not Poisson. It's probably something else. Let's assume it's Poisson. All right. Also, we know that this link service rate is exactly 1.5 megabit per second. All right, which means that the service rate, if I assume that the packets are exactly 500, it's deterministic. It's not a stochastic. It's a deterministic process. But again, I'm going to simplify, assume that it's going to be a stochastic process. So I'm going to assume it's MM1 queue. Okay, so you're going in with your eyes open saying, let me just get a ballpark, okay, what's going on. And that's what it's good for. It's a good ballpark estimate of the number of packets in the queue. So probably queue has one packet. What you're going to do is that the link, how do you find this out? Well, this is just nothing more than P1. Okay, sorry, one packet is, should I say in the system or in the queue? so one packet in the queue is P2, because P2 means we have one packet in service, one packet in the system. So we have one packet in the queue means P2. So we need lambda. So lambda is 300 packets per second, so we know that. What about mu? Well, a packet size is 500 bytes or 4,000 bits. Okay, over 1.5 megabits per second turns out to be the other way around, 1 over mu. So mu is 375 packets per second. Okay? Now, it's deterministic actually, but we're going to assume that it's actually a Poisson process with a mean of 375 packets per second. Then we can immediately see that rho equals 300 over 375 equals 0.8. Okay? So that's essentially all we need is rho, because as I said, the only thing that we care about for Pj is rho. So we can now say that P2 equals 0.8 square, rho squared times 1 minus 0.8, 1 minus rho, and that's equal to 0.128. Okay, so there's like a 12% probability that we're going to be having one packet in the queue. It's illustrative to look at P10, which is 10 packets in the queue. That's 0.8 to the power 10 times 1 minus 0.2, and I don't know, it's approximately 10 to the minus 7 or something like that. I don't know. Does anybody have, because I have a wrong number in my notes here. Does anybody have their notes handy? It's the latest version of the notes has the right value in there. So 10 to the minus 7, 10 to the minus 8. What is it?
Yes, the old one.
You're the old one. Anybody have the latest version? It's small. Okay, whatever it is, it's whatever. So what we're saying is that even with a load of 0.8, 80% capacity, it's a pretty heavily loaded link. You're not even going to have 10 packets in the queue. How many is 10 packets? 10 packets is 5,000 bytes. Okay, 5,000 bytes is what? 9 packets. Sorry, yeah, 9 packets is okay. So 4,500 bytes. Sorry, you're right. P10 is 9 packets in the queue. It's not a lot. It's like 5 kilobytes. Okay, 5 kilobytes of buffering costs you nothing, right? You don't need megabytes and megabytes of buffering. Even with just 5 kilobytes of buffering, the probability of packet loss is basically practically zero. Okay, so this is a pretty strong result, because your CIO of the company says, oh, my load is 80%, am I going to have packet losses because it's a heavily loaded link? You say, well, assuming it's MM1, I can tell you the probability of packet loss, even if you put in let's be very conservative and let's say I'm going to give you 100 kilobytes of buffering, okay, just as a ballpark. There's no way you're going to overrun 100 kilobytes, okay, even with the 80% loaded link. Okay, that's a pretty strong result, and we got that by the whole MM1 analysis. Now, one could argue that this is not really MM1, things will be different and so on. So that's why we have what's called the engineering correction factor of 20. Okay, okay, I did the MM1 queue. I know it's not correct. Well, let's just make it 20 times, because the cost of 100 kilobytes versus cost of 5 kilobytes is like nothing. 100 kilobytes costs, I don't know, few pennies. I don't know how much it costs. In fact, you can't even buy 100 kilobytes of RAM these days, as far as I know. They'll only sell you 1 megabyte at a time, probably. So you just say, well, my analysis indicates it's very, very low probability of going beyond, 10. And if you think about 100, it's even lower. So let me just multiply a factor of 20, and it doesn't cost me very much. I'll just stick it in, no problem. Okay, and this is basically how queue sizing is done on the internet today. Okay, this is it. There's no more than this. You say, MM1 says this, let me multiply it by, if you're Cisco, you multiply by 100. If you're Huawei, you multiply by 20, depending on how cheap you want your stuff to make it. And then you'll say, okay, this is the amount of RAM I'm going to stick in here. And guess what? It works. Okay. What MM1 is doing for us here is to give us a reasonable idea of what to expect. It's giving us a reasonable idea that, okay, 4,500 bytes is already reasonably good. And so we can kind of use that as a metric to size things out. Okay? So I'm just giving you a sort of practical example of how one uses these mathematical techniques. So I'm an engineer by training, so I'm doing math not because I like it, but I also want to use it, right? That's what I want you guys to also think about. We're not doing Markov analysis because it's fun. We're doing it because it's fun and because we know how to use it now. We can do something practical with it. Okay, that's really, to me, the more interesting part. Not only that we can do all this nice math, but at the end of it, we come up with a number, something we can actually use when sizing buffers. Okay, it makes sense. Because otherwise, what would you do? Somebody says my load is 80%. How many buffers do I use? Do you say, well, should I put 1 megabyte or 10 megabyte? And same thing, by the way, is true for CPU sizing. You have a desktop and you kind of say, okay, what processor should I use? Today the answer is buy the most expensive, buy the fastest processor you can buy. Because, you never know what your load is going to be. But if you were to assume that it is following some kind of Markov or MM1 type distribution with job arrivals and job services, maybe you'll find that the probability that you have a waiting list of jobs, in your run queue, in your scheduler, being more than 2 or 5, be very small. Then you say, why do I need a fast processor? I can decrease the service time. I can have mu to be smaller and still not have any problems because my row is like 0.3. My row is 0.3. Probability of having a large queue is very, very small. So why do I worry about it, right? So it gives you some sizing considerations for CPUs as well. And arguably that's a good thing to do because a slower processor means less energy, right? So you're actually using fewer watts, fewer cooling costs, and if you take a data center with 100,000 processors in there, well, maybe you don't need 100,000 processors. Maybe you can do it all with 2,000 processors by increasing utilization of each one, right? We had a talk by Irfan Ahmed about virtualization. So what they was doing there was saying, okay, let's virtualize everything. We can move everything into one piece, and then as jobs come, we can expand it out again and contract it out again. All that analysis is based on the MM1 Queue over here. And for those of you who saw Professor Wong's presentation at the Lecture13 seminar, it used exactly this analysis to dynamically resize the number of processors allocated to a job in a data center to reduce the energy consumption. So all of these are actually related techniques. Okay, any questions about this over here? Okay, let me pause here, and then I'm going to come back to the mean number of customers and mean waiting times, and maybe we'll get to MM1 in MM infinity. What we want to do is to compute the number of the mean number of customers in the queue. So we call that n bar. And this is nothing more than sigma j equals 0 to infinity j pj, right? That's obviously what it is. There's a definition of mean. And that's why I said if you know pj, you can get everything else you want. And this is nothing more than sigma j equals 0 to infinity j rho to the j 1 minus rho. And this equals rho over 1 minus rho. Am I getting this right? Pj, I think, yeah, pj is, yeah, rho to the j, not rho to the k. So it turns out to be rho over 1 minus rho. Okay? Nice mathematical result. What does it mean? Well, it means something quite interesting and quite dramatic and quite non-intuitive. Okay? What it says is that the mean number of customers in the queue, if I were to draw it at the 0, 1, and this is rho, actually I can go beyond 1, I suppose, is that it goes something like this. If this is 1, it asymptotes to infinity at 1. Okay? Why? Because the denominator is going to 0 as rho goes. And of course, if you go beyond 1, you're out of luck anyway. So, two very important points. The first point is that if we have a link at high utilization, we're going to get essentially expected number of queue customers in the queue to be infinite. Okay, it's going to be infinite. So we never want to have the utilization go very high. Okay, so the typical operating point is like 0.7. Okay, people use 0.7 or 0.6 or 0.8, but we never want the utilization of any link to be above 0.7. We can actually sort of model this in the following way. You know, we define this. You can think of it as being essentially flat up to 0.7, and then you have high load until about 0.9, and then after that it's infinite after 0.9. Okay, I mean that's a reasonable approximation to this. And so when a network operator wants to size their network, they'll say we want to keep all our links in the range below 0.7. Okay, again we're using MM1 analysis as a rough and ready guide, and any link that's in 0.7 to 0.9 is thought to be congested. Okay, it has a lot of load. We have non-trivial number of customers in the queue. Non-trivial meaning non-zero. Okay, and anything about 0.9, you're in danger zone. Okay, you're like green, yellow, and red. So this is green, this is yellow, that's red. If you're above 0.9, you really have to go and increase the link capacity. You could increase more service rate or reduce the arrival rate. How do you reduce the arrival rate? You tell people not to use BitTorrent, or you charge them for it. Okay, that's how you reduce the arrival rate. So that's what Comcast is doing. This is what all net neutrality is all about. Okay, net neutrality debate follows from the fact that heavy users push the link into the 0.9 and above range, which means that you have to reduce lambda. And the way you reduce lambda is to pick on the guys who are responsible for the load. There's no point in picking on the people who are sending 1 or 2 packets here and there. If you're sending lots and lots of packets, you better reduce the load. So the whole net neutrality debate actually follows from MM1. Okay, in some sense. So that's the first important point, which is a sizing guideline. You want to keep your queues below 0.7, and if you're in 0.7 to 0.9, you better watch out. The second thing that's important from this is something that's non-intuitive. It actually doesn't make any sense at all when you think about it, which is that when rho equals, say, 0.9, lambda equals 0.9 mu. Okay? All right? So let's think about that. That means my arrival rate is actually less than my service rate. It's only 90% of my service rate, yet I have a large queue. Okay? Or let's take even 0.95 to make it even more important. Okay? So what's going on? Because intuitively, you would think that if my arrival rate is less than my service rate, if lambda is less than mu, then the queue should not be very large. Right? If lambda is less than mu, queue shouldn't be very large. So why is it going on? So again, you're a Tim Hortons manager, and you say, yeah, my servers can serve on average 1 customer every minute. And the arrival rate is only 0.95 customers per minute. Okay? So why am I seeing long queues? What's going on over here? Okay? So to understand this, you have to remember that lambda is not a deterministic process. It's a stochastic process. So when somebody says that lambda is 0.95 mu, something like this, so if you look at time, and we look at the actual values of lambda and mu, okay, we draw like this. Obviously, mu has to be greater than lambda, so it looks something like that. And lambda is something like that as well. It's a stochastic process. Okay, or maybe I shouldn't call it lambda and mu are changing. Lambda and mu are the long-term rates. Let me just call it lambda t and mu t, okay, the instantaneous arrival and service rate, so you're not confused about it. But the point is that there are burst arrivals. Okay, there are 5 people who come out from a class, they all arrive at the Tim Hortons at the same time. The long-term arrival rate is still lambda, okay, and to some first approximation, we can still think of this as a Poisson process, okay, because we can say, you know, it's still Poisson. We can still be, even in a Poisson process, we can have burst arrivals. There's nothing that says that if the arrival rate lambda is small, we can't have rapid transitions over here in this direction, because it's a stochastic process. We don't know. We only have probabilities. So even in a Poisson process, it's possible for a lot of people to show up. If a lot of people show up, the population size gets large, and then it gets shrunk down only at the rate mu. Again, we can have rapid diminishings of the queue as well because of large queue, mu. But there is an inherent asymmetry. And the inherent asymmetry is that when the queue is at 0 process, okay, in the 0 state, we can have more arrivals, but we can't have more departures. There is no mu 0. There's only mu lambda 0, right? Because there is no mu 0, that means that when a burst arrives, it's sitting in the queue, okay, and we start serving them. Okay, we start serving them one by one. And then when they get to 0, it's possible that we could have sort of a burst of service credits, okay? But when the queue is 0, we can't build up service credits. We can't sit there and say, okay, I've done the service already, okay? You don't have that. So in other words, it's on the ingress side, you can have stuff come in as bursts, but when you get to 0 state, you can't build up service credits, okay? You can't just sit there and say, okay, I've done the work already. And because of this, you have this asymmetry. Stuff can come in at lambda, but it can't go out at the actual service rate mu because we don't have any service when the queue is 0. Okay? Does that make sense? Does that make sense here? So we have this stuff comes in at lambda, but mu has to be larger, quite a bit larger than lambda, for you to be in this range, for you to be clearing out the queue. Otherwise, the queue is in this bad state where you have a burst of arrivals, but not all of them are not served. So by the time the next burst comes, we still have people in the queue. Okay, the queue is not fully cleared because mu is not large enough. Okay, and as I said, the opposite side is that when you have burst of clearings of the queue and you get to 0, you can do nothing. You just sit there and say, I have no work to do, so I can't use up that service credit. Okay, so this asymmetry means that in a stochastic process, if it's deterministic, by the way, if lambda is less than mu, that's all we need. We can have lambda equals 0.9999 mu. It's deterministic, q will be 0 or 1. It's exactly matched. But in stochastic process, we have this notion of build-up and decay, and so we absolutely need mu to be a little bit larger than lambda, quite a bit larger than lambda. We should have rho less than 0.7 over here, as I said, for things to work out properly. And now the nice thing is that, so intuitively at first you say if lambda is less than mu, life is great. Okay? What queuing theory tells us and what MM1 theory tells us is that no, we need to have mu to be a little bit larger than lambda, and we derived everything on this purely from, almost everything from first principles. We derived this from the analysis of birth death process, and this value over here and this analysis over here is essentially a complete analysis. Okay? And that is the beauty of this. Okay? By understanding the meaning of stochastic process and by going through the analysis, we can now look at a practical phenomenon, which is lambda is 0.9 mu, and we find long queues. Okay? And so that's the explanation going on over here. So I think it's a very interesting phenomenon. And it's true for any queuing discipline that if lambda is close to mu, then we're going to have congestion. We're going to have the link queues build up. And we always need a little bit of room. Okay? Again, to go to a hypothetical ISP, the CEO of the ISP, obviously CEOs are mathematically ignorant. So they'll say, wait a minute, you're running that link at 80% capacity. Why don't you run at 100% capacity, right? But you don't want anything. Why are you wasting 20%? The answer is we're not wasting 20%. We have to run it at 80% or 70% capacity because we have this phenomenon going on over here, okay? And it's not a deterministic process. When you have this, stochastic process requires a little bit of headroom to clear the bursts that are building up. Okay, so one has to be careful because when somebody says, I'm only using 80% of my time, okay, that it feels like, okay, wasting 20%, okay, which is true. If I'm saying I'm working on my research 80% of the time, that means 20% just goofing off, right? Whereas if I'm saying a link is busy 80% of the time, it means that it has capacity to absorb bursts, and we don't want an infinite queue to build up. So that's why these two meanings of utilization have to be differently modeled. The link is not goofing off. Okay, the link has to have idle capacity in order to prevent queues from growing very large. Any questions about this over here?
Is it possible to define your mu with respect to the amount of time spent in the P0 state?
Yeah, you can just.
For example, like it's important. Like if
yeah.
you're in the P0 state,
yeah.
They would spend their time actually building credit by making more coffee.
Right.
But then your mean service time actually decreases.
Yes. Correct. Yeah, you mean you can start coming with the service disciplines where if you're in the P0 state, arrivals, the next k arrivals after P0 state actually have a mu higher than normal mu, right? You could sort of have a birth death process. It gets messy because you have to know how long you've been in P0 state.
That'd still be
No. No, because you're saying that, because we need the departure process to be identical in every state. Yeah. You could view it as probably a tandem MM1s, a series of MM1 queues with some probabilities between these subchains. It could be done. I haven't thought about it. But yeah, it would be worth, yeah, you could probably do it. Yeah. Okay. All right, what about the mean waiting time in a queue? So this is the mean number of customers. How about the mean waiting time? So W bar, what am I using over here? I guess I'm not even calling it anything. Okay. Well, clearly the mean waiting time is related to the mean number of customers. And what's the relationship? Well, it's just Little's law. So we know that the mean waiting time, okay, so mean number of customers equals mean waiting time times arrival rate. So obviously mean waiting time is mean number of customers divided by the arrival rate. The mean number of customers we already know is rho over 1 minus rho, right? So you divide that by lambda. This is nothing more than lambda over mu over 1 minus rho times lambda, which is 1 over mu over 1 minus rho. Okay, just a simple analysis over here. And so it's related clearly to the same thing. Basically, you have the denominator 1 minus rho. So if you draw this graph, same thing. Waiting time also kind of goes up more or less the same way, which is what you'd expect. Yeah?
And what is the mean number of customers
In the system. You're right. Thank you. I keep making that mistake. Thank you. So it's one off, okay? So in the limit, it doesn't really matter. What we're really interested in is the behavior in the limit. So mean waiting time, similar kind of distribution over here. The reason why I brought up mean waiting time is because I wanted to actually illustrate something else, which is that we can use Little's law. Okay? So we get this from just sigma j pj, right? And once we get this, we can plug it into here to get mean waiting time as well. This is true for all queues. I can take any queue, and I can tell you what pj is, and then at that point, you can compute this to find the mean number of customers. Then you can use Little's law to tell you the mean waiting time. So you get 3 parameters of interest right away, or 2 parameters of interest right away. Mean number of customers and mean waiting time you get over here. And if I can tell you the probability of being in any particular state. And so what we'll do, I guess in the next time, is look at MM infinity and MM1 K queues. It's bonded buffers and infinite number of servers. And we'll use this trick of just saying what pj is, and then we can compute all the other parameters of interest from pj. So this is what I mean, parameters of interest. Okay. Any questions about this over here? Okay, so I want to just recap what we did. So the started out with this general equilibrium solution for a birth-death process, which is in terms of absolutely arbitrary arrival rates, lambda I to any state I. And we showed that convergence, or we stated that convergence happens if after some value of j, the arrival rate is less than the service rate, and then it get convergence. We did the Kendall notation and showed that MM1 Queue is nothing more than a birth-death process with arrival rate lambda in every state and the service rate mu in every state, except in state 0. Okay, there's nothing to be served over there. That's a fundamental asymmetry over there. And given that it's MM1 Queue, we computed the equilibrium probability of being in a state. This just follows right out from the general equilibrium solution. It's actually easier. And then we computed these 2 parameters, mean number of customers and mean waiting time, and showed that they both diverge, go to infinity once you're beyond 0.9 or something like that. And that gives us some good intuition into how queues behave. It shows that there is asymmetry, and it gives us some rules on what to do when the queue gets beyond around 0.7. You should get more service. Okay, so some sizing rules, what are called provisioning rules for traffic management in computer networks. Okay, all right. So we'll stop here, and then next time we'll talk about these last few topics in queuing theory.